confusion. Yes, I don't know if that created any confusion of any sort, but the idea was that it's really about external principle, which you might have seen in many of these contests, but it's to motivate some kind of philosophy which underlies different variants of this kind of idea. So the idea is that this is sort of abstract. I like to use this word, but it's overused in our country. So I say concept, which takes forms in many different ways of thinking about problems. Sometimes you end up thinking of this as really algorithms. Sometimes as maybe induction, more specifically, strong induction. Sometimes you end up thinking of this as what? Maximal objects. Maximal / maximum. And we'll get to the distinction between these two in a minute. Things. So by things, I mean something more combinatorial like vertex, a clique, matching, something like that, something which is maximal. And the idea is that you might have seen some problems of this form where, the solution starts with look at the largest thing, it satisfies something, and then with that thing, you're able to solve the problem. So what I mean by that is, let's pick a very standard problem and see if people are familiar with this and see what the typical solution looks like and try to see what the intuition behind it is. So let's pick a classic problem. So let's say you have endpoints on the plane in general position. So by general position, I mean no three are collinear. Then there exists ABC among them, such that the circumcircular triangle ABC contains all of the remaining points. So what does a typical proof look like if people have seen this problem before? If you're not seen this, you can try this and think about this for a minute. You feel free to share your ideas. I don't just want to talk to an empty screen for 1.5 hours. So feel free to share your ideas. If you've seen the solution, just like go over what a solution looks like for this problem. And if you're not seeing this, like think about this, let me know any ideas you have. Anyone? I don't want to be too silent.
Consider the circumcircle with the largest area.
Largest area, okay.
Or covers the most points.
Covers the most points. How do you finish then?
If there's something outside, then swapping one of these with that one would cover the new one.
Exactly. So something outside, you just cover more things. Yes, that's when we're doing it. One common proof typically looks like this. This is the one I'm more familiar with writing out. Is that you just
consider the largest angle.
Yeah. So you consider the largest possible angle or the smallest possible angle because you want to make the circle big. So either way, largest, smallest, same thing. And you try to make sure all points lie on the same side of this line. All the points are here. And then if this is the smallest angle, then this circle will contain all of these points. And that's how one argument goes. So formally, you'd write this as pick two consecutive points on the convex hull, pick the smallest angle they make, take the circumcircle. And that's the proof. And this is a very artificial proof. It's like anyone who says this proof is like not explaining what they thought of while coming up with this problem. So it's very common to see these kinds of proofs in textbooks of Olympic combinatorics or some kind of APS post. And yeah, if you've not seen these things before, there's no way of knowing where this is coming from. It's just like someone came up with this, and you have to believe this. This is how you do things. But there's a okay. What's the PDF go? Wait a minute. Okay, just a second. I'm confused with my thing. Just give me a second. Strange. I'm not familiar with this. Yeah, okay. I should be able to retrieve this now. Yeah, okay, fine. So how do you try to solve this kind of problem? This is what I wanted to do earlier, this thing. So how do you try to solve such a problem is the real question here. And well, the idea is that let's start with a small case for this problem. Let's start with 4 points. So you have A, B, C, D. And how do you solve it for A, B, C, D? Because now you're trying to solve the problem and not trying to do the standard thing. We're trying to see what the mechanism behind the standard thing is. So if you just have A, B, C, D, how do you pick things? Well, one approach is that you can pick, say, something like A and C. And if B and D add to more than 180, then you can pick this thing. Or you could have picked B and D, and if A and C add to more than 180, you can do this thing, the other thing. So that's one way of thinking about this. But that's not very natural, right? Because you have to make a choice. You have to switch between these two. So looking at the angles add to more than 180 is one approach, but that leads to multiple configurations. But if you only look at the base BC and try to see that, okay, if this angle is really small, then this circle will contain this one. So the idea of putting things on the same side and looking at the circle, which has the smaller angle, makes more sense when you're doing it just for 4. So like that's the only thing you should do for 4 if you want to avoid all ambiguity. Because then instead of picking BC, you could have picked another thing. Similarly, if this was concave like this, you could have still done this thing. So the idea in general is that if you have a side and you have a point here, as long as you have a point which has a smaller angle, you can take that point instead. And if you have another small point, you can take that thing instead. And you keep doing this until you end up at where you can't do this anymore. And if you can't do this anymore, isn't it obvious to figure as it then just restrict each other to be inside the circumcircle? Yes. So okay, if you have seen enough of these things, then this is obvious. I agree. This is not a hard problem by any stretch. I'm not trying to claim this is hard. The point is that there's a certain way of thinking which underlies these ideas, and I'm trying to sort of reconstruct it from here.
So you're trying to motivate these ideas.
Trying to not just motivate, but show how this is canonically the correct way of thinking about this in many cases, not in all cases. Like even in this case, for instance, even if you just want to look at the external thing, because it's natural, right? You want a big circle. But the idea is that how do you, if you don't have any intuition for angles or circles, why would you think of the big circles? So it's like, okay, just start with the smallest thing, and each time you can pick a new thing. Is kind of the idea.
So you're trying to use greedy algorithm.
Yes. So this is a kind of greedy algorithm, kind of extremal thing, or whatever you want to call it. My point is that all of the things I mentioned in the previous slide, like previous page, greedy algorithm, strong induction, maximal objects, all of these come from the same thing. They're not different things. So like,
yes.
And this I'd later call something with chains. I'll link it with this as well. So we'll get into this. I'm just trying to pick a very light example so everyone's happy with it. And so the idea is that you can pick circle 1, you can pick circle 2, you can pick circle 3, and you can keep doing this, and you have only finitely many points. You'll end up hitting a stopping point. And the only thing you need to make sure was that these are all the points are on this side. You don't want any point on the other side, because then this thing doesn't work. So that's the only thing you have to make sure. And that's how you come up with this kind of proof. So that's one argument. The general idea of this kind of maximal principle is not that you look at a problem and you say, I want to look at the largest clique, or that I want to look at the largest matching, or that I want to look at the largest connected subgraph, or whatever. You don't start with a problem saying, I want to look at the largest thing. The point is you look at the small things which have some structure. So you look at some smaller objects, and you build from each of them. So you pick small objects and you build each of them. Typically, these objects are like some kind of set with some condition, and the arrows are just containment. So that's the typical structure of these problems. And the point is that eventually you end up hitting a stopping point. So you end up hitting some CK and you can't go any further. So why is not being able to go for any further important? That's important because now you have conditions on the CK. Like all the other things, if you could have just extended, there's no structure to them. So each of these C1, C2 don't have any structure to them. Once you've hit CK, you have some concrete thing. You know that this angle is the smallest angle. The angle that this makes here is the smallest possible angle. So this is kind of the idea of this kind of algorithm, is that you start with something, you keep building new configurations, you end up at a largest configuration in some sense, and from there you can't do anything else. And because you can't do anything else, that forces conditions on that thing. And so that often motivates what this kind of large structure is. Sometimes you don't even know what structures you're looking for. Here it was obvious you're looking at triangles and circles, but sometimes you don't know what structures you're looking for. And that's when having this notion that you're trying to build something big helps pick out what the structure was originally. So we'll see a lot of that in some of the problems we'll do. And I wanted to say maybe one more thing, which is like just a paradigm for this thing, is that maximal objects come from, well, not always, but most of the times they come from end goal. So it's like you build a chain, and this is usually the final object in the chain. And that's how you gain all such information. And another thing I wanted to say about this was, this is a kind of thing which has meaning beyond just combinatorics and beyond just Olympiad problems. So my motivation for doing this kind of talk was, funnily enough, not from combinatorics, but from something in combinatorial algebra, some kind of argument there, which seems to be a natural way of looking at maximal like ideals, as they call them. And from and that intuition carries over in combinatorics, is what I realized, and I thought this is perhaps a good way of thinking about maximal objects. So okay, instead of going on too much about this philosophy, I'll pick something which is an actual problem. And so here's a problem. So let's say you have 2n plus 1 people in a party, satisfying the following condition: for any group that exists person who knows them all. So knowing is mutual, you know, if A knows B, B knows A, it's basically a graph. Prove that there exists who knows everyone else. So a pretty standard kind of context flow. So you have 2n plus 1 people in a party, and for any group of n people, there exists a person who knows all of them. So you have to prove that there exists someone who knows everyone else. And I think this is a good starting problem to see this kind of idea coming. So I'd like people to think about this, throw any ideas you have, don't hesitate, talk about it.
We can probably just do something very global,
Really?
like do
So-
something very global, as in
It would be something like proving among any group of k people, for k greater than n, there will exist a person who knows all of those other people in that group. Maybe we
Yeah.
can inductively prove that.
Okay, so you're saying in any group of n plus 1 people, let's say there would be someone outside this group who knows all of them. Is that your claim?
Yeah, like within that n plus 1 people.
Within that n plus 1 people, someone knows all of them. Okay. I'm not sure I follow your claim. So are you saying that given n plus 1 people, there exists someone inside this group who knows all of them, or someone outside this group who knows all of them?
Someone inside that group, like we are given this base case of n.
Right. Oh, and for the other remaining n, you can do
Maybe.
something like that. I don't see how it works, but that's a good idea. Let's think about that. And someone said you wanted to do something global. So I'd like to ask you, why would you want to do something global? What's your trigger for looking at global here?
Because you have some people who know like a lot of people. You can probably sum them and get that someone has to know a lot of people.
Maybe. So I don't know if global works or not. So if you think it works, I'll recommend trying it out. But I don't know if it works or not. Does the person know himself? I think many philosophers have tried to answer that and have failed. So we'll just assume they don't. And does the person have to be a part of the N people? No. So this is necessarily someone outside the group of N people. Yeah, so I like some of the ideas here. So someone says, you want to look at this globally, like add, but how do you do this globally is something I'm still not sure about, because in my mind, there's like lots of subsets, right? Like if you pick random collections of N people, there's like 2n+1 choose N of these collections. And you're doing some kind of counting using that, which seems like a very big coefficient to beat. Maybe it still works because 2n+1 choose N+1 is similar, but I don't know if that works or not. So if you see an approach, let me know. I don't know if that works or not. So what are some other ideas? Everyone just like throw ideas. You don't
Consider the one
you don't have to always
who knows most people.
look at the one who knows most people. Makes sense, right? Like if you want, okay, so what do you want to do with this? Let's see. So you pick P who knows the largest number of people, because it makes sense, right? You want someone to know everyone. So you want someone who knows as many people as possible and then show that this is everyone. So let's say P knows M people. Okay. And M is the largest possible. So you can also assume M is at least N. Now you want to show that this M is equal to 2N. So let's say there's someone P does not know. How do you move from here?
I guess like take n-1 people from M and Q.
You take n-1 people from N, people from here, call them like, I don't know, P1 to Pn-1. So it seems very discriminatory to call them by numbers, but okay. So you have Q, P1, Pn-1. Okay. And there exists someone who knows all of them.
Then that could be like PN or someone. It doesn't have to still be P.
Oh, sorry, I don't understand. That could be what?
Like PN or someone else from that group of M people.
Right.
The person who knows all N of these people.
Yeah. In which case, Pn knows P and it knows n-1 other people and it knows Q. So that will be a contradiction. If Pn is like someone in this group, then that will be a contradiction. Yes. So, but Pn can also be outside this group as well, right? So in which case, it only knows N people. So that's not a contradiction. So I agree. If Pn were inside this group, then you would be done. I agree with that.
Wait, why is it a contradiction if it's inside?
If Pn is in, so if Pn is inside this group, then Pn knows P. It knows n-1 of the P1 to Pn-1 people, and it also knows Q, right? So then it knows and yeah.
But M
You
is
might know
not.
more
Errors in
people.
yeah, fine. Okay, there might be more people in P, so that's also not a contradiction. Fair, actually fair. So yeah, we're not getting much leave out of this, but I think this is a good idea. This is going somewhere good. So this is a very nice idea, right? You want to look at a person who knows the largest number of people. Okay, I want to hear more ideas. I think this is a good idea. Someone also said we want to somehow separate them in n+1 and N and somehow argue one person knows people in both groups. Any other ideas? Go at it.
Knowing each other is mutual.
If I know you do, yes. Yes, knowing is mutual. It's just a graph with edges, nothing complicated. Okay, but let's say if it were just a case that if m were equal to n, if you didn't have more things, then Pn being inside would be a contradiction, let's say. So that also I think is a hint to something, like there's some other structure which is missing here. Hmm. Okay.
Wait, if nobody knows
Wait, can we
everybody,
just now take these Pn minus 1 and P?
Sorry.
Can't we just take numbers from P1 to Pn minus 1 and P?
Okay.
Then there exists a person who knows all of them, right?
Yes, but that person only knows n
But
people.
that person also knows P. So
Yes.
it restricts it to be Pn.
But if you just pick P1 to Pn minus 1, let's say,
Yes.
and you pick a person Q over here who knows all of them. So Q knows n people and P knows this many people, right? So it's still not enough.
Like I'm saying consider the set P1 to Pn.
Okay.
That is all the people P knows.
Okay. Okay.
So
So
like, yes,
P knows P1 to Pn.
yes.
Okay. Sure. Then
no, but P might know more people.
you might know more people, and also you can't pick like the condition only says for any group of n people, right? Like you can't pick like a group of n plus 1 people and then say someone outside. So there's
Okay.
some restriction there. But again, this is leading somewhere. Like this idea of looking at the person outside, which has edges, is telling you a hint towards some structure. So I think all
Also,
of
what
them
about like an independent set?
also, so people who don't
Like
know
the
each other.
largest independent set here.
Okay, so largest number of people who don't know each other, let's say. Let's call them Q1, QL. Okay. So they have no edges between each other. Then you have
Yeah.
some.
So like, okay, no, that doesn't give that much.
Mhm. Okay, so firstly, one small hint, one small reduction. If for any group of n people there exists someone outside, you can't always say that for any group of n plus 1 people there exists someone outside. But you can say for some other numbers apart from n and n plus 1, right? You can say the same thing for all numbers less than n, for example. So any group of n minus 1 people, there still exists someone outside that group who knows all of them.
Yeah.
Yeah, so that's an obvious reduction. So that just tells you that you don't need to always pick groups of size n, you just need to pick groups no more than n. Okay. Does that help you collect these structures? So we have a bunch of ideas here. Some of the ideas are like we look at existing sets and we pull out some new person who knows all of them. And another idea is that we want to find a person who knows n plus 1 outside and over here. So try to combine these two ideas and see what kind of structure you need. Or just like work with small cases. Let's work with n equals 1, for example, in which case I think this is fairly obvious. If this is n equals 1, you just have 1, 2, 3, and you have something like 1, 2, and 2 and 3 know each other, so 2 knows everyone. So n equals 1 is obvious. Try to do n equals 2, let's say, and see what you observe. I think in this problem, doing small cases would help find something. I want people to find the structure on their own to see what the idea is.
I think for n is equal to 2, we can use a global idea.
Okay, so what's the global idea?
So like we have 5 number of people.
We have 5 people, yes, and
And we
then-
can, and then the number of pairings will be 10.
yes,
So for any pair, we have that one person knows that pair, knows
yes,
everyone in that pair.
okay,
And since there are 10 such pairs, so they map to 10 such objects, and we can only select them to be 3. So there is exactly one person who knows like 3 pairs of people, but that isn't.
10 and 5. There would be someone who knows 2 pairs of people, but then those pairs need not be disjoint, right?
Yes, yes. I'm
could
saying
you-
about 3 pairs of people.
So about 3 pairs of people,
Yes,
No,
because there are like 10
10
pairs,
pairs, and
and
5
we
people.
can take like 3 people. Only 3 people can map to that 10 pairs. Like any 3 people, it can be in any case.
Right.
So we would get that at least one person knows like 4 pairs by
4
PHP.
pairs.
Yes, because 10 by 3, 10 is equal to 3 into 3 plus 1.
Yes, but okay.
Then if you consider any 4 pair, you would just get that. You would just get. Wait, doesn't work. It then just gives that there is one person who knows all the other 4 people,
Right.
and we are just then done.
Right. Okay. I believe this.
But I
might
guess
check this.
extending this idea won't work because it would be really counting.
Right. Like I'm the only reason I'm suspicious of this idea is because 2n plus 1 choose n is very big. So unless you have
Yes.
like 2n plus 1 choose n plus 1 coming somewhere, you won't be able to sort of match this bound in some way. Like I feel the bound is just kind of very big. And also just to have some intuition, this graph should have almost it should have a large number of edges. I won't say it has all the edges, but it has close to all the edges in some sense. So this is a very big graph. Like there are very few missing things in this graph.
What if we just look at the biggest clique?
Okay. And why would you want to do that?
Because if there are too many things outside the clique, then you have a problem. Like if the clique is too
Yeah.
small,
Then
then
you can
if it has
extend.
like say at most n, then
You
you can
extend
find
it.
something outside connected to all and make it bigger.
Exactly. So this is what I was trying to go for. I'm sure there are other ways which should work. This is just like one approach I was going for is that. So let's say you start with one. The reason I say you can do it for smaller numbers is that let's say you start with one person. Then you can always find someone who knows this person. Then you can find someone who knows both of these people. Then you can find someone who knows all 3 of these people. And so on. So what you get is something called a clique, where so you get up to k people, let's say, and all of these k people know each other.
That k can be extended to be n easily.
Yes, that k can be extended to be. So this algorithm of adding a new person can only be done as long as k is less equals n. So when k equals n, you can still add one more person, and that gives you an n plus 1 clique. And now's the magic is that if you pick so you pick the remaining n people.
Oh, and one person will.
One
have to
person
know
from the
that.
clique knows
Yeah,
this.
one person.
Yeah, it has to be someone from the clique only,
Yes.
which just raises it again.
Yes, exactly. So we notice how we combine 2 ideas. One of the ideas was adding new people to this existing set of people we had and seeing how big this can get. And the other idea was using the remaining n plus 1 people and sort of finding a different person. The only reason this argument works is because if you have a clique here, let's say, if you have a bunch of people outside, the point is that earlier you could only say one person among this group knows them, which wouldn't be enough to conclude. But the point is that this person also knows everyone in their own group as well. So this is combining 2 ideas. In the previous picture, we had some missing edges. But if you were constructing this set algorithmically, you would not have missing edges. Like if you were constructing this set from the ground up, there would not be any missing edges here. You would have all of these will be edges too. And so unless it just strikes you to look at the maximal clique, there's a very natural way of also looking at the maximal clique, which is that you build your set in a very natural way, which is keep adding new people according to your condition. Because in some sense, this is the only thing you can do. Like this is the only operation the problem allows you to do. And the point is that the maximal object, if that does not work, then anything else should not work as well. So there's a certain optimality to assuming this. And at the end, when you do have a clique and you have people outside, you can just combine the two arguments together. So this was one example I wanted to show, which is like a very transparent example of why you should look at maximal objects and chains. Because it's, if a solution just starts with pick the maximal clique, I don't think it's very clear why you would think of the maximal clique. But if you play around these edges and you realize that there are missing edges, that you need more of these things over here, then it makes more sense to look at these maximal cliques, because then you're building the structure from ground up. And the clique is only, clique of size n+1 is just a natural byproduct of what you were doing. So this is one example I wanted to talk about. And is this clear? Is the example clear? Do people understand this? Any questions about this? Or about the idea and anything? Yeah. Is there something?
I didn't exactly understand how you can go from a 3 clique to a 4 clique.
Okay, so point is, let's say you have 3 people who know each other. And let's say 3 is less equal to n. Then your condition says that given n people, there was someone outside, right? So if you just have 3 people, that's not enough for the condition. Just add
Okay,
like
got you. Okay,
any
got
n
you.
minus 3 people.
Yeah, got you.
Yeah, and then you can pull out a new person who knows them. So and then that person can be fused with them. So yeah, in a sense, what you did was you took your condition, you looked at all possible weaknesses of your condition. Instead of looking at the hypothesis for n, you looked at it for 1 to n minus 1 as well, because you could, right? Like there's nothing stopping you from doing that. And then you build a structure which there's also nothing stopping you from building this group of friends, right? This massive group of friends. And then when you have to stop, then you ask yourself, this is the best you could have done. Like there's nothing else to do. And if this doesn't work, then the problem should be false. And indeed it is false. If you just had like instead of 2+1 people in this condition, if you had like 2+2 people, you could probably just like have a clique, have 2 separate cliques, and that will be a counterexample of some kind. So you can probably just like tweak this around to get a counterexample if you just had a different number. And this is in a way showing that there's a quality case which is very strong. There's a chain which is very strong. There's a principle of you want to build things and it becomes maximal, which is very strong. All of this works very well in this problem. So okay, if people are okay with this problem, I can also give you the next one if that's okay. And if you want source, this was Russia 2000 something, 2000, what was it? 2001. Yeah. Oh, I don't know what the Elmo 5 is for this year. Like I've not done Elmos for a couple of years now, so I have no idea what the problem is, but it's great if you find something which relates to this. I think the general idea is that once you see enough of these examples in the form of not just looking at it as some magical, I looked at the longest possible sequence or whatever, then you end up having this intuition for all kinds of problems. So my idea is that this principle is very universal. It's very ubiquitous. It's found everywhere. And it motivates many different things which look very different. So having a class on greedy algorithms or induction or recursion or something like picking maximal matchings by itself is not very important to me. Like the idea is that this is a very general theme which counts. So okay, we can, if everyone's okay with this, we can move to the next problem. If you have a question, feel free to ask. So I'm just writing the next one. If you have any question, feel free to ask. Like I'm just writing this down. Okay, so is everyone okay with the first one? So we have the new problem now. So you have 20 members of some tennis club have scheduled 14 matches, and the match is like a 2-person game, with each member playing at least once. So everyone gets to play at least once, otherwise it wouldn't be much of a club. And you have to prove that there exist 6 of the matches with 12 different people playing them. So all 6 of these matches have different players in them. You have to prove that there exists such 6 matches out of the 14. Ideas, just like don't be scared to throw ideas. If you have anything, just go at it.
Largest perfect matching, and the outside would be independent.
Why would you look at this though? I mean, in this problem, I think it's pretty reasonable to look at this, but yeah, that is correct. So the problem statement kind of gives it away that you want 6 matches which are different. So if you just look at this as a graph where people are vertices, and so you have like V1, V20, and the matches are edges. So let's say if V1 plays V3, then you have an edge between them. Then finding 6 matches which don't have endpoints in common would be same as finding 6 things like this. 6, right? Yeah, 6 things like this. All the endpoints are distinct. And you want to find 6 such edges. How do you, so what's the natural thing to look at is, well, what's the largest such collection of edges? Just keep adding, like here, there's nothing stopping you from adding things as well. Previously also, there was nothing which stopped you from adding a new person. There's nothing stopping you from adding a new edge as long as you can. So I just keep adding edges.
But then we'll need to prove that it stops at 6 edges.
Yes. So you need to prove that this stops at 6. So let's say you are able to draw k edges. And you have like say V1 to V, and I'll just give them some names. Vk plus 1, Vk to V2k. Let's say these are the k edges you're able to draw. And you can't draw any more edges. Like this is the constraint you have. So you get something called a maximal matching. Which is slightly different from something called a maximum matching. And sometimes the difference is important, sometimes it's not. I'll get into the difference later as a minor point, but let's just solve the problem first. So it's natural to look at as many edges as you can draw, which are all different and don't have common endpoints. What's the catch here? So what condition do you have after you have drawn these k edges? What can you say?
Like then we
The rest of the graph should be an independent set. So we'll get an independent size of set of size at least 10.
Yes. So rest of the graph is independent. Rest. Is independent. And the point is that if you pick any person V here, then if we had any edge which was not ending at any of these 2k vertices, you'd be in a big trouble because then you'd have k plus 1 edges. So all edges which come from V have to end in one of these things. And that's okay. So that tells you something. How do you count from here? I mean, that's still not the maximal part of the problem, but that's still a good part of the problem.
And we also
and then
can't like
all other vertices would have at least k degree.
All the vertices would have at least
K degree.
Sorry, I don't follow why.
Like because then each of the vertices would be connected to V1, V2, Vk or any.
It'll be connected to something over there, but not necessarily all of them, right? Like it is a constraint on number of matches. There's a very small number of matches which are being played.
Yes, they are.
So how do you count this?
and we also have that if V1 and V3 are attached in the perfect matching, then
Yes.
V1 and V3 can't be attached to 2 different vertices in the independent set.
Yes, they can't be attached to 2 different things. So you can't have this and you can't have this. You can't have both of them have outside edges. Yes. Things like that. So, and you have to show what you want is k is at least 6. This is what you want. So now, what do you have? So it's just standard counting now. So it's like, okay, you have 20 people total. So you have 20 minus 2k outside vertices. And you have 14 minus k remaining edges. Okay. What can you say? Each remaining edge has at most one outside vertex. Does that make sense?
You have 20 minus 2k plus k, which is greater than equal to 15.
Yes. So 20 minus 2k is 14 minus. Sorry, no, not greater equals to. Sorry. No, sorry, what did you say again? 15.
20 minus 2k plus k, that
Plus
would
k.
be greater than equal to 15. Because
Why?
k is less than equal to 5.
Yes, okay, let's assume k less than 5. Okay. Then you have 20 minus k is greater equals 15. Okay. You see why this is finished then?
What?
Sorry?
This finishes, right? Because you have
Yes.
k edges.
Yes.
Okay.
Yes. I was just asking everyone if you see why this finishes. Because again, it's still minor counting, but this kind of counting with maximum things is important later on. So if you assume this, then you end up getting this kind of inequality, which you only have 14 matches. So you can't have this. Okay. So anyone has any questions with this? Again, I think both of these examples, the first one was slightly trickier, but both of these examples have one thing in common, is that nothing is stopping you from adding a new thing. Like you can always just add new things and it'll be fine. So if you wanted to construct a clique, there was nothing stopping you as long as you ran out of the condition itself. And here, if you wanted to construct a matching, there's nothing stopping you. You just had to analyze what happens once you have stopped. One minor point I would make is that sometimes it's better to just take the maximum object instead of the maximals. Can someone tell me the difference between? Okay, so can someone tell me the difference between maximal and maximum objects? So seems like an English difference, but sometimes there's a maths difference as well. Like in this case, it was better to take the maximum matching instead of the maximal matching. And do you see why? Not that it makes any difference. I think proof works both ways. But do you see why it's better to take the maximum object sometimes? So let's
What
pick
was
an-
the maximal matching again?
So maximal matching is you keep adding edges until so it's a set of edges when it's a matching, and you can't add more edges to it so that it remains matching. Maximum is that among such collections, you still pick the largest one. So here's an example of this. Instead of matching,
Okay.
instead of matchings, I'll pick something else. I'll pick a different example to make this better understood. Which is there. Okay, so this is a very messy diagram, but you have a set of 3 vertices, a set of 2 vertices, and a set of 4 vertices. So all of them are independent sets, right? Like this is an independent set. This is an independent set. This is an independent set. But all of them have different sizes. So if you pick a maximal thing, you could have picked any of them. You could have picked the one with 2, you could have picked the one with 3, you could have picked the one with 4. But if you pick the maximum thing, you always have to pick the one with 4. That's the only syntactical difference between doing these things, is that sometimes when you're really sure that the largest object has to work, it just makes sense to take the largest one. Like, don't even shy out with picking the largest in the chain. Just pick the largest one across all chains. So in this problem, for example, we just wanted 6 matches, right? We didn't care any structure about this, whatever structure was there. So it just makes sense to pick all of them as pick the largest possible collection instead of like a smaller collection, which is still maximal. Both would work, but the largest collection is just the easiest pick here. And similarly in this one, if once you realize you have to pick a clique, and for that you have to do some kind of building, I guess, it just makes sense to pick the maximum clique itself. So usually, if you pick either of them, usually it does not matter, but it's important to know that there's still some difference there. The maximum is the largest among the maximal objects.
Is there time you would prefer using the maximal matching or
that?
maximal something?
Maximal something. Sorry, what? Is that?
Is there like a time you would prefer something which is maximal instead of maximal?
I think it's more like maximal is how you want to think about. If you don't know what the object should be, then you should think about it in a maximal way so that you can build the object. If you know what the object should be and you're very sure that the largest object has to work, otherwise there's something wrong, then it just makes sense to pick the maximum object itself.
Like we use maximal to build the maximum in some way.
Exactly, in some sense, yes. That's a very good way of putting it, is that you use the maximal construction. And if once you have the construction and you're very confident this is going to work, just pick the largest thing and just don't even worry about it. So sometimes there's a problem where the largest thing itself may not work and you have to pick a specific maximal thing. It depends on how hard the problem is, but it's just a way of thinking in some sense. Instead of a technique which solves problems, it's a way of looking at a problem.
All right.
Yes. Generally, I think most complex problems I can recall, but I've not done too many, would be if you take either, it doesn't really matter much. But sometimes the difference is important. So it's worth knowing that there is a difference. For example, I think, I'm not sure about this proof. I may have forgotten this. But when you try to prove Hall's marriage lemma, it is easier to do it with just picking the maximum matching instead of arguing with some maximal thing. Like the maximal thing can get you in trouble sometimes in some proofs. Whereas if you just pick the largest matching, or if you just do some kind of strong induction, it's a lot better. So in this case, that I think works better. This is one example I can think of. But again, if it turns out that both are still equivalent in this, then, or it doesn't really matter, then sure, that's also fine. Yeah, another thing would be strong induction, which is just that, again, with strong induction, you're assuming all the possible things you have. So the idea is that you keep doing every possible thing you can. And when you can't do anymore, then you start asking questions. You don't ask questions before that. So that's a very philosophical way of looking at it, I guess. Let's make another question if you're okay with this one. Also, the previous one was from USMO 89. I think, yeah. So it's the previous one. Just giving sources in case someone's curious where these are coming from. Okay, so let's pick another problem. Let's say you have a set S of size n, and you have 3 element subsets. So 3 element subsets A1 to AM. You don't know what M is. You know that AI intersection AJ is at most one element. And you know that what's the other condition? Not the condition. No, I think these are all the conditions. Yeah. So prove and there exists a subset.
Did you introduce? Sorry to say, I was like
Sorry, what?
for 5 minutes. Did you introduce Hall's lemma right now?
Sorry, what?
Did you introduce Hall's marriage lemma before this?
No. I'm just mentioning that as like something where if you try to prove it using maximum matching, it becomes a bit more convenient to argue, I think. But I don't think there's still a significant
And what
difference.
are A1 to AM?
Oh, just 3 element subsets of S.
Okay.
Yeah. So there exists subset X inside S such that X is at least make it integer part. And
That condition is true for every single I comma j.
Yes, for all I and j.
Okay, okay.
So no two of these three element sets have two elements in common. That's given to you. So you have to prove that there exists a subset of size root 2n, forget the floor and all, which does not contain any of these three element things. So try thinking about this as well. I think all of these three examples are of a very similar flavor, where there's nothing stopping you from doing what you want.
We have to include the maximal in somewhere and then just prove that it has to be greater than, like it stops at floor
Yeah,
of root 2 and
exactly.
just
So this is kind of a joke question in some sense, right? It's like the only way of picking such set has to pick the largest such set. Like there's literally nothing else you can do. You don't even have to think of building this set, because if the largest set does not work, then none of these sets work. So that's just a very meta way of looking at the problem and being like, you have to pick the largest set. Let's pick largest X.
like because such X is in existence. If it wasn't, then we could
Right.
just build.
Yeah, and of course it exists, right? Like there is like some pick a one element set that does not contain any three element set. So like some subsets exist, pick the largest subset, because if the largest does not work, then none of them work. So sometimes it's just forced on you. Sometimes picking the largest thing is like, you don't have to even build it up. It's just there. Like if you see it, you know that this is the only thing which can work. And that is often the motivation for greedy algorithm, is that you know that the largest thing has to work. So you just pick as much as you can and then argue after that, rather than try to think about the structure beforehand. So let's say this X has k elements. Okay, now you have these k elements v1 to ek. Say, I don't know, just 1 to k. I'm not taking a vertices, so it's fine. And you have remaining n minus k numbers. And if you pick any remaining among them, you pick anything x over here. And because this x is largest, you can't add this little x to big X. So the moment you add it, something has to give, some problem has to arise. And the moment you add it, some problem arises if you have two y and z over here, such that xyz is one of these AIs. So the moment you pick some x outside this k element set, you find a pair of things inside this k element set which makes a triple with it. And no two triples have more than one element in common, so these pairs will always be distinct. You can't always, you can't have two x's giving the same pair. So that automatically gives you that n minus k less equals k choose 2, which gives the bound. So is this okay with everyone?
Sorry, but I don't follow.
Yeah, okay, so I'll slow down a bit. So let's say X has these k elements, and you have n minus k remaining elements, let's say. Now, if you pick something which is outside X and you try to push it inside X, you try to say that my X is largest. What happens if I push something inside the largest? It can't satisfy the condition anymore, right? Because that's why it is the largest. So if it can't satisfy the condition anymore, then there must be some y and z inside X, such that XYZ forms a triple AI. Right? So each X gives you some pair among the first k elements. And no two different values of X will give you the same pair y and z, because no two of these three element sets over here have more than one element in common. So no two of these values of X will give you the same y and z, which means that for every X you get a unique pair. So you have n minus k such possible X's, and you have at most k choose 2 pairs, and each of them goes there uniquely. So you have n minus k is at most k choose 2, which you can solve to get like k squared plus k is greater equals 2n, and you get something like this.
Right.
So that's just calculation. But the main idea is that once you have the set, you know that there can't be anything else. So the only point of this problem is to realize that once you have the largest thing, what do you do with the largest thing is you try to break the largestness by throwing in a new element. You try to break its maximality, and that can't happen. So something has to
It
be
was
forced.
just counting here.
Yeah, it is just counting after that. But again, if you're new to this, I think it's good to see that the counting itself is not the hard part. The hard part is realizing that this is the only
We
thing you
had
can
to
do.
took the maximum was the main part, right?
Right. It's like it's not even something where it's a contract solution. Like this is the only thing you can do. This is like a forced thing on you. So it's like the problem itself forces that this is the most natural thing you can do. And that just happens to work, because if this doesn't work, then nothing else can work. So this is one advantage of picking the maximum, for example. If you just pick the maximal x, you would still get the proof, but you won't have the mental surety that if the maximal fails, then some other sets can't work. So that's like a very syntactical difference. It's not a practical difference. Okay, so is everyone okay with this? Because now I can pick a problem which is not supposed to be done in this way, but I think that will be a good example of when you have to actually do something where there's obstruction. Like here, there was no obstruction to just picking the largest thing. Here, there was no obstruction to picking the largest bunch of edges. Here, there was no obstruction to picking the largest clique. So I might want to pick a problem where there are some obstructions. So do people want to see them?
Yeah.
Okay. So on the previous one, and the source was something like Italy something, TST, 2000 something, 5. Question mark, because I'm not very sure. Also, just give me a second. Just give me a second. I'll be back in 1 minute. Yeah, sorry about that. So, is everyone okay with the previous ones?
Yes.
Yeah.
Okay, so let's pick a problem which does not have this obvious way of transforming things. And again, this problem I should preface is not how it's supposed to be done. Like there are other easier approaches. This is just one way of looking at it. So this is 2014 C1. And you have endpoints inside rectangle R. No two of them line parallel. Also, someone's chat. Okay, fair. So if you're doing it, you probably realize that this doesn't have much in common with algorithmics. There's like other more natural solutions, but this is, I guess, one way of showing how abstraction comes in practice in a very creative way. So two of them lie on the line parallel to a side of the rectangle. Okay. So R is dissected into key rectangles. With sides parallel to R. Such that no point in the strict interior, I guess interior, but same thing. Ooh. Okay, so you have a big rectangle R. This is a possible rectangle, and you have a bunch of points inside. Let's say you have 3 points inside. And these points are such that if you join any of them, they do not form a line parallel to either axis. Okay, so, and your job is to split this into a bunch of rectangles. So you can do something like this. So you split this into a bunch of rectangles. All of them have sides parallel to sides of R, and each of the marked points is not in the interior of any rectangle. So it is on the edges. Okay, and you have to prove that you need at least n+1 rectangles. So here there are 6 rectangles and 3 points, which is way too many. So what's the optimal obvious thing which you can do, which is if you have, say, 3 points. This is the equality case, right? This is just the obvious equality case, right? Where there's just 4 rectangles straight up, no complicated things. So this is the equality, like the obvious equality case. There might be more contrived equality cases sometimes. So I think this was what stumped people when this came in a TST long back. Was there's a strange equality case like this as well. So for 4 points, you have this 5 rectangles for these 4 points, and it's not the standard equality case. There's a strange equality case as well. And so how do you think about proving this? So I want to lead you
Can
towards one solution.
like I have done it
Yeah.
before, so I won't say.
Yeah. And if you have a global solution, I don't want that. So that's also a constraint I'm putting on you. Is like the official solution is something like you count corners, you count lines, and something shows up. So I don't want you
Yes,
to
the
do that. I want
official
you to do
solution
something.
is global.
Yeah, it's global, but I want you to do something local, something without any of that. Think about how you want to transform something like this into something like this. Is where I want to lead you towards. Just to show you how powerful this can be, is that you can actually just change the rules of a problem and still be fine with it. Like that's how
Wait,
powerful
can
this
I
can be.
can I try this with the
Yeah,
local
sure.
thing?
Yeah, sure.
So
Think about
so
this.
so can we can take the largest rectangle that is formed in there.
Largest rectangle.
Like
Okay.
you have this. We will extend all the lines. We will not keep them as line segments. We will keep them as they intersect the.
Yes. Yes. So you don't care about whether this is a line segment because the condition just tells you that
We have to draw lines, not lines.
exactly. You just care about the lines itself because your condition says no two of them lie on a line parallel to a side. So even if they're like this and some other segment and this, that's not valid. So you just care about the whole line. You don't care about the segments. That's
And then we can take the largest rectangle.
largest rectangle. What do you mean by that? Area wise or how?
Area wise.
Okay.
By
But that-
these lines only.
I don't think that matters though, right? Because for example, if you have this configuration, let's say this 5 thing.
Yes,
Okay,
yes, that doesn't work.
You can just like adjust the sides of each of them and like the configuration is basically the same.
Yes.
So not quite the largest, but like something about you want to tweak these rectangles into in some way. And lines is a good observation. Now you don't care about the. So in some sense.
Now, like we will get some k horizontal lines and
right.
m vertical lines. Each these k map to some k-1 k such that these they will form k+1 rectangles in there, and these m will form m+1 rectangles.
So, something like that. So you can count them and do some kind of global thing, and I'm sure that it can work. Like it probably works as well.
Yes.
But I want to show something which is surprising, which is very strange, which is not obvious that this should work. So, for example, here's another observation: is that if you have, in some sense, any set of rectangles which form these lines is not different from this, for example. Like they form the same lines. So you can have more rectangles, you can have less rectangles, but the lines are the same. So having more rectangles is a bit useless. You want to minimize those rectangles so that you still have the same set of lines. So the claim is more about lines than about rectangles. So what is the obvious thing you have? Can you say something obvious?
You need at least n lines.
Yes. If you have n points, then you need at least n lines because pigeonhole principle, right? Okay, so n points, you need at least n lines. No, that became limes, okay, whatever, but and if you have k rectangles, you can observe by looking at many such pictures, you get at least k-1 lines. Or you get not at least, at most k-1 lines. So you get n less equals k-1 will follow if you can show this claim. If you can show that the k rectangles you get at most k-1 lines, then you'll get k is at least n plus 1. Okay, so this is like some reduction. Now we only care, so we don't care about the points now. We have removed all the marked points completely, and we don't even care about the rectangles, we just care about the lines and how many rectangles are there. Okay, so if you have n lines, you want at least n plus 1 rectangle, something like that. Now notice something, if you have a rectangle split in two like this, you can usually get rid of this, right? You can just fuse them into one rectangle. And that should not be a
Yes.
problem, right?
Yes.
Because you lose at least one rectangle, like you lose exactly one rectangle when you do this, and you lose at most one line, so that's not an issue. Okay, so, or something like m lines by m plus 1 rectangles. Whatever. Okay, so this is not an issue. Something like this would be very strange though. Like how do you change anything about this? So that is a strange case we don't know. What's another case you can change? What's another obvious case you can change?
The horizontal.
Horizontal.
Horizontal. Sorry, what do you mean? Oh, like this?
Yes.
Yeah, but like they're the same for me, like same orientation. But so this is a different case, right? Like these and these are very different from each other. And this, it's not very clear what you do with this one.
Can't we just extend the lines?
Yes, that's an idea, but when you do that, this splits into, instead of reducing the number of rectangles, the number of rectangles increases, right? Like you have this and this,
Yes.
and you transform it into this, this, and this. You get one extra rectangle. You want like, you don't want to increase rectangles, you want to lower rectangles if possible. So there's a problem in doing this. But when is this not a problem?
When they are stacked perfectly.
Exactly, when they're stacked perfectly. So if it's something like this, it's not a problem. Then you can do this plus this, right?
Yes. And then we can easily convert it.
And then you can convert it. But you won't always find things like this. You're more likely to find things like these. So how do you find things like these? How do you find these things? Like these aren't always going to be there. So what's the right thing to look at?
We
They
can
will
just
be,
extend
right?
one
The
line.
final diagram.
Which one?
In the
The one that
final
doesn't
diagram,
touches the rectangle.
One that doesn't what?
Like there are these two rectangles and one
Yeah.
is standing on the top of it. Then the leftmost vertical line, we
Right.
can just extend it. It will not obstruct anything in there.
Yes. So I don't fully understand what you mean though. Leftmost vertical line in this one.
Yes, yes.
Yeah, this one we're not playing with, right? Like it still stays here.
Okay.
Like we are only cutting out this one and extending it to be this one. So if you're cutting one line and drawing a bit further, but you're not losing any lines in the process because this whole line stays. And this whole line stays. So we're doing some kind of surgery, but we're not losing any information in this.
choose the rectangle on the bottom left,
Bottom
and
left,
then you can do that again and again.
but
You'll get you can make the rectangle smaller because you can cut it throughout the
but if this is your bottom left, let's say,
horizontal.
if this is
Okay.
your bottom left, you can't extend it over here, right? Like you can't stretch it out.
Okay.
But you can do it with this one instead, like instead of the bottom left. So you can reduce the bottom left to be this new one. So then the new picture,
Yeah.
you have this is the new bottom left. So
And we
what's
can
the
keep
correct?
doing that.
You can keep doing
We
that.
can choose the smaller
Exactly.
rectangle.
And so you keep doing this, so you pick the smallest rectangle in the bottom row. So you pick the bottom row, pick the smallest rectangle.
So in the end, it has to reduce.
Yes. And then you keep extending this. and eventually you'll just get a line, like this is your rectangle, and you can just like chop off this line and lose one rectangle and one line at the same time. So in effect, when you do this algorithm over the whole configuration, you'll have reduced any configuration like this into a configuration like this. So
It's a bit hard to think like this in a global problem.
yes, it is. And I'm not saying this is a recommended way, but I can tell you that this kind of thinking is very powerful, for example. So
This is more instructive though.
yeah, this is very instructive, I think. And also just like, I'll give you an example of things where sometimes even I think the global solution is a bit more non-intuitive unless you have some experience.
Yes, it is just a bit of calculations.
Right. So if you want something which extends this idea, try this one. So try this problem at home if you want. And it takes the same idea, but I think the global solution is a bit more complicated for this. It's not counting, you have to think a little bit more. Whereas this solution works extremely well if you do even more imaginative things. So you have to do something like you slice the board in two, you put together the pieces, you do some magic with that. And the amazing thing is that all of that works because you have some freedom and you have some extremal objects to work with. So here again, if a solution started to pick the smallest object, like pick the smallest rectangle in the bottom row, then do this nonsense, then chop out the line and then argue otherwise, that'd be very, very crazy. Like no one would believe that this is fine. But this is a very natural way of looking at it. If you're looking at it this way, I think there are other ways of looking at it which are more efficient. But if you're looking at it in the sense of you want to change all diagrams to the equality case, then this is a very natural approach, I think. But yeah, I think I would recommend trying this as a follow-up problem of a similar flavor, the RMM problem. So I'll pick something else as well. Let's pick a new problem. If anyone has any questions on the previous one, let me know. Any questions on this one? Everyone okay? If everyone's okay, we can move on to the next one, or I can wait for like a minute if it's fine. Also, just let me know if you're finding this too easy or too tricky or anything in the middle, because I have other problems as well. Like this is just like some subset of problems I have to use for this. So if you want, I can change the difficulty accordingly. Anyone? Too easy, too hard, anything in the middle?
It's fine, I think.
Okay. Okay, then I'll go with the ones I had in mind. So maybe pick a slightly more complex example. I only did this a few days back, so I don't fully remember this that very well, but okay, let's try this problem. I think this is a fun problem. So you have 998 cities, which should tell you which country this is from, because only one country likes this kind of strange number. And you have two-way flights between these cities, which is a very strange way of saying graph. And of course, between any two cities, at most one, there's at most one flight because it's a very strange place. And for any k cities, let's equal to 5k plus 10 flights. Between these k cities. So now what you have to prove is that, let's say there are m less than 5,000 flights total. Then you can keep adding flights. Such that this condition still stays true. And condition is true, and you have 5,000 total flights. So they're explicitly asking you for an algorithm. Just like somehow you have these 998 cities, you have any k cities, at most 5k plus 10 flights between them, and you have less than 5,000 flights in total. So you can keep adding flights between cities such that you have 5,000 total flights at the end of it, and the previous condition is still true after the process. After you've done all this adding new flights, the previous condition is still true. So prove that you can do this.
5K plus 10 between them or overall?
Between them, like so, among the k choose 2 possible flights, 5k plus 10 at most.
Okay.
So I guess correct thing would be maximum of k choose 2 at most. No, minimum of, yeah. So yeah, less equals both of them. Yeah, at most k choose 2 flights, of course, but if k is large enough, then k choose 2 is too big. So you have at most 5k plus 10 flights then. What's this? I realize this is very terribly written. I'm not used to writing on Apple Pencil.
It's from this year's only, right?
Yes, this is Russia 2022. So I like this problem. I did this a few days back. It's a pretty cool problem. Similar idea. Maybe I guess there are probably other ways of thinking about this, but I was thinking about this unit, so I just had this idea. So again, thoughts, ideas, observations, go for it. This is a good problem. There's many ideas.
Sorry, but was the K fixed?
No, so for any k.
Okay.
Any k cities, you have this condition. So even for the whole graph, you have this condition which gives you this thing. And then you can keep adding things to make it actually 5,000 and still have this condition be true everywhere. Don't worry too much about the 5 and 10, they're random constants. I think that doesn't really matter much. Also, just for okay, what happened? Okay, yeah, just note this thing is so just to be clear, this is also the same number, not some random 5,000. So ideas? Anyone? Okay, to start with, so how about this? Why don't you just keep adding edges as long as you can? Like, let's just do a very abstract thing, but we don't even care how our algorithm does it. Just add an edge if you can. If it satisfies, if all the conditions stay true, just keep adding edges. And then you claim you reach 5,000. That seems like the only thing which can work, right? Is everyone okay with that?
Yes.
Okay. Keep adding edges till everything is okay. Then what are things you should consider for that? So, okay. So this is a strange argument, right? Because you're saying there's some abstract way of just keep on adding edges as long as your conditions are true. So you're looking for a maximal configuration of some kind. It's not even clear what the structure is. Like a maximal n cities with less equals 5n plus 10 flights or something. I don't know. So it's a strange maximal object, but like that's the idea. You just keep adding edges as long as you can. And it's reasonable to think, it's not forced on you that this is going to work necessarily. Like there might be some clever way of adding edges which is slightly better than this. But it is reasonable to assume that this should be optimal, right? Because you don't know anything about these K clusters or what the graph structure is, what the edges are. You don't know anything else besides these local bounds. So it's reasonable to believe that this is going to work. Or rather, if this is not going to work, then something really wrong is going on. So it's worth considering even if it's not going to work. Okay, so what do you get after this? So first question. Why stop? Why can't you add a new edge? Like, let's say I have added the maximal possible number of edges. Why can't I add a new edge? What's stopping you from adding a new edge? Anyone? Is the question clear? That okay, I keep adding edges and I have to stop because I have to stop. There's only finitely many things. But why can't I add a new edge after that? What's stopping you from doing that?
In every group of K cities, you will have 5K plus 10 edges.
Every group of K cities is probably not how you want to say that. I don't think that's always true. But what is true is that if you add an edge, there exists some group of K cities for which this thing breaks.
Yeah.
Yes. So I don't think it's even true that for every K group you have this. But
Yeah, okay.
what's certainly true is that if you add an edge, something has to break somewhere. Maybe many things break at the same time. But so, and the answer is something breaks. So if something breaks, then what happens? So if I add an edge UV, let's say, then there must be some collection of K cities or vertices, whatever, which contains U and V, which had already reached 5K plus 10 edges. So if you have some collection which has already reached 5K plus 10 edges, that is a bit more delicate. Like you can't just mess with those collections. Every other collection you can always add, but like if you add an edge, some collection goes wrong somewhere. So there's a bunch of objects. Like it's not very clear. Again, this is a very good problem for this kind of structure because there's no clear structure. It's not a clique, it's not a matching, it's not an independent set or whatever. It's just some subgraph which has some edge condition. So it's a very loose object. Like we don't really know what this object looks like, but we know that there's a bunch of these objects which can break if you add a new edge. So what can you observe about? So what's a special object to consider among all these things, among all these subgraphs? The only ones you should consider are these, right? Ones which already have reached their optimal number of edges, because everything else can be tweaked with and is not causing problems. The only thing which is causing problems are these 5K plus 10 things. So it's called, come up with an adjective. I don't want to say call a subgroup good, like come up with some fun adjective. Anyone? First good adjective gets on the paper.
Dead.
Also got dead. Morbid. Okay, I'll replace this with morbid. If has
Interconnected would be a better word.
connected would have been interconnected or something would have been better, but morbid is like a very unfortunate label for them, but okay. If it has 5K plus 10 edges, fine. So you have these morbid subgraphs. This sounds wrong, but what do you do with them? What's so now you're instead of working with vertices, you're working with these clusters of morbid subgraphs which have these 5K plus 10 edges. How do you look at them?
I guess I have a global idea, but I should not say that.
The union of vertices of all those graphs will have all the vertices.
Okay, I'll go to the second idea first, but first idea I think is refutable. Like I don't believe there's a global here, but if you have a global idea,
Yes, it would fail.
yeah, like I think the global idea is for this problem especially, I think global is just not going to work because there's no symmetry, right? Like there's just any structure can happen locally.
Yes, yes.
So global is not very strong for this. And yeah, the second idea was, I think, basically correct. So the idea is that if you have two morbid things, let's say A and B are both morbid, then A union B is also morbid, is the claim. So A and B were some sort of maximal objects. It's reasonable to assume that when you fuse them together, you should still get a maximal object.
You can just like choose some from B and then choose some from A. They are morbid, and this usually works, right?
Which one?
Like you can choose some elements from B and some elements from A, and
Yeah.
it would then work.
Yeah, so
They
you can't
would
have like,
also have morbid
yeah, exactly.
subgraph.
Right. And also another thing which okay, if you pick a vertex from A, a vertex from B, the subgraph which breaks does not have to be a subset of A union B, right? Like it can have things outside A union B as well.
Yes.
So it's not very obvious that you can just pick a vertex from A and B and then the condition breaks. Because the subgraph corresponding to that edge could just be like something outside A union B along with that edge. So it's still a little bit more work to show that A union B also has this condition, but it's not that bad. Like I think it's a fun combinatorial way of looking at unions. Like what do you, when you're counting about something about a union, what do you usually think? And that's going to be the answer. So if you have A union B and you want to count anything about A union B, how do you count it usually?
PIE.
Yeah, so that's kind of what you do here as well. Is that so number of edges in A union B would be number of edges in A plus number of edges in B. There are no issues with cross edges. So you remove A intersection B, like the common. So A intersection B itself, you remove that. And that is at most 5 times its size plus 10. So A union B, so at least. When I say mod, I mean the number of edges. Yeah. Minus. And each of this is 5 times the number, B plus 10, number B plus 10. Which is 5 times A union B plus 10. So it's greater or equal to this 5 times its size plus 10, but it can't be greater because we are always satisfying the condition for all things.
And we just needed this.
Yeah, so this is an equality, yeah. 5 times the number plus 10 edges. So also morbid. Okay. So A and B also has this condition, which means that if all of these clusters you have can just be fused into one big cluster. It's like all of these clusters are just one big thing, and this is your maximal object. Like you realize what's going on here, right? Like
And we can just then extend
Yeah.
K to be 998.
Exactly. So okay, there's still a little bit more work here to do there, but this is roughly the idea: is that you have a bunch of these small clusters, and you can fuse all of them together. So each of these clusters was a maximal object which we got from the greedy algorithm, and we can just fuse all of them together. It's like even bigger. Like this whole thing is now an object. It's still not clear why this covers all the vertices though. So let's say this is like this whole thing is A, and now you have vertex B outside A. Now you can do the vertex and edge argument because there shouldn't be anything to outside this.
Yes, we can do the same argument as
Exactly. If you add an edge and something breaks,
Yes.
then you can fuse it with A again. So we will get subsumed by A. So now you can do the exactly.
We can just use these two processes and then get
Exactly. So like this one vertex and this whole A collection, just pick something. If there are things outside the union as well, we don't care because all of that gets fused with A. So when all of this gets fused with A, you just end up with A is everything now. Becomes all vertices. And that's how you finish this proof. So any questions about this one? I think this was a good example for me. I did this a few days back, and because you do greedy algorithm to get clusters once, which is like one kind of maximal object, then you do some kind of fusing between them to get a very big object, and then you argue that this is the thing you really want. So it's like kind of combining the chain idea twice in some sense. I like this a lot. Any questions? Is because we went through this a bit fast. If there's any confusion, let me know. Is everyone okay with this?
Yes,
Okay, so I had one more problem.
but I guess can you just skim
Yeah.
through the solution again?
Okay, I'll just skim through this argument here. Okay, so firstly, the idea is that you keep adding edges till you no longer can. So this is by the way a whole sketch. It's like there are a few more details you should probably check, but the idea is that you keep adding edges till you no longer can, and then you ask yourself, why can't you add more edges? And turns out that if you add a new edge, it'll have to break something, right? Otherwise, you can always add it by your assumption.
Yes.
So something breaks, and if something breaks, what that means is that if you add this edge,
It is either it forms some clusters or some vertex and a cluster thing.
Yeah.
Right.
So I probably should have said cluster instead of these morbid set, but yeah, cluster is probably the right term for this. So it has to be part of some cluster which has exactly 5 times the size plus 10 edges. So look at those clusters specifically now. And the point is that if you take A and B as 2 such clusters, you can do a counting by kind of argument to show that A union B has at least 5 times the size plus 10 edges. But because we already did our algorithm in a way where nothing ever breaks, so it can't be greater than 5 times the size plus 10, which means it has to be equal. And if it is equal, then you get that this thing is also clustered. So if you have 2 clusters, you can fuse them to get a bigger cluster. And so you can fuse all clusters to get a big thing called A. And if there's any vertex outside A, you can use this vertex and something inside A when you're putting an edge, and fuse them all together as well to subsume this inside A, which means that there are no vertices outside A. A is all the vertices, which means that there are 5 times the size of A plus 10 edges at the end, because A is a cluster. So at the end, you have 5,000 edges in total. So is everyone okay with this? There are a few things you should check, because you need to, at the last step, you need to worry about the degree of V a little bit, because you have to do something like k choose 2, whether it's bigger than 5k plus 10 or smaller than this, depending on the size of the cluster. So there are a few small details to check, but this is roughly what the solution looks like. So if everyone's okay with this, I had another one, but I think everyone would have seen this problem by now. So this was the magician problem on the last year's item or last year's item, whichever was the magician problem with the cards.
It was on 2021.
2021, yeah, whichever was.
And it was proposed by you.
Yeah, yeah. So I had that problem as well, but I'm guessing people have seen it. So I don't know if you want to discuss that or if that's okay. That also had this.
Yes, we can discuss that.
Oh, if you want, we can discuss that as well then.
But that got traveled by Oris.
True, but I don't think anyone knew about Oris lemma, so it's probably fine. So I'm using a different folder for this. I'll totally shift folders later on. 2 points on it. Yeah. Oh yeah. I don't know what the scheme for that was. Like I wanted there to be like some points for guessing the strategy. Like just take one thing and check it with others. That's one thing. But there's a huge trap there, which is kind of what's fun about these problems is that there's a trap where you don't realize what the magician has to do. Like you just argue that magician can't do any better. So it's probably worth discussing that, even if it's a tangential idea. So okay, so I'll probably source the previous one. Yeah, source the previous one. This is 2021. So do people have the problem with them, or should I just like write the problem again? Okay,
You just write it again.
Okay, let's write this. So magician, detective, arithmetic, play a game. What's the game? So game is you have a deck of cards 1 to 52, and you don't know, so they're all face down. So detective does not know which card is which. In a move, the detective can ask detective can pick a pair. And ask if they're consecutive. So you can pick a pair of cards and ask if they're consecutive. And What's the other thing? Okay, so here, yeah. So after, what's the smallest number of questions? After which you can point to here and be sure it is they're consecutive. Okay, so that's the question. So you have 1 to 52 cards face down. You can pick a pair and ask if they're consecutive, and of course you get truthful answers. And at the end, you have to determine, you're done with your questioning, you have to pick a pair and say that these two have to be consecutive. So what's the smallest possible number of questions you have to make, after which you can surely do this? And these kind of questions
51.
trick people up. 51.
No,
Yeah,
no,
51 would be
50.
the last. Yeah, so it's like 50 questions, and then at the 51
Yes.
you can claim. Yes. So one strategy is obvious. You just pick like card number 1, whichever you.
The construction is really easy.
Yeah, very obvious. Just like pick one card
Yes.
and then just check it with all but one cards. And if you keep getting no's, then the last one has to be consecutive. So because there is something consecutive to this card. Typically, you have to be very unlucky to get it even all the way down to one less card. You'll probably get it done in even smaller moves, but worst possible case is to get it in 50 moves. So strategy for okay, 50 moves. And well, of course, the detective just has to go around looking for clues. That's easy. The magician has to come up with the actual trick, right? So how do you prove that he can't do it the detective can't do it in under 50 moves? So strategy for magician. So I'll let people tell me what does it mean for magician to have a strategy, because that's also kind of tricky if you've not seen it before. What does this even mean? What's the strategy for a magician?
He just keeps saying no and then hopes that at the end he's able to order the cards in some.
Exactly. So it's a very fun idea to me, because it's like, this is not something you're taught in school, and it's like you can keep playing this game, and at the end you can just lie about all your answers, as long as at the end there exists some configuration for which your answers are correct, and then you can just claim, oh, that was my configuration all along. So he can do that. He can just answer no to every question until it's just impossible to do so. So that is his strategy. Say no as long as possible.
Can we just try to make this problem approach through a graph theoretic approach?
Yeah. So we'll just make this a graph very quickly, don't worry about it. So say no as long as possible. And sometimes you can even make another simplifying assumption. This is never necessary, but it's always just fun to write. Is that, so suppose he can only say no as long as possible, and he can say it for m less equals 49 turns or something. Then the detective turns out to be very generous, and it's like, okay, if you actually fell short of 49, I'll just make blank questions and make it 49. So you can just actually assume it's exactly 49. You can, instead of less than or equal to 49. So you can even add more simplifying assumptions. So this is a very funny simplification. It's never necessary, but it's fun to do. So you can assume makes 49 moves and has to guess. Now, jargon aside, let's just make it a graph problem, because that's what we are here for. So let's make it n vertices instead of cards, or like 1 to n numbers, and n minus 2 questions. So I'll draw an edge between I and j if and only if they are consecutive. So if and only these vertices are consecutive in the natural number ordering. And oh no, sorry. I'll draw an edge between I and j if and only if it has never been asked. So out of so if you look at the complete graph on n vertices, let's say something like this. Out of these, the detective asks some questions. He'll ask some questions, and I'll cut off those edges. whichever question he asks, I'll remove that edge. And whatever the graph remains at the end, so after removing n minus 2 edges, if you can label this graph from 1 to n in an order where 1 is connected to 2, 2 is connected to 3, and so on, if you can find a Hamiltonian path in this graph, that will be his answer. So the magician can do this thing where he can just be like, okay, I had this kn, you remove these n minus 2 edges of your space, and it'll always have a Hamiltonian path, and that'll always be my answer. It's like, okay, this is actually the 1 to n ordering and not anything else I thought of before. And that would be his strategy. So if you just prove this graph theoretic claim, you're done with the problem. So it doesn't have anything to do with suspicious magicians and suspicious detectives anymore. It's just a graph problem where if you have kn and you remove n minus 2 edges, then you always have a path from 1 to n. So is everyone okay with this much?
Yes.
Everyone comfortable with this? Okay, I'll just assume everyone's comfortable with this. If there are any questions, feel free to interrupt me whenever you want. And okay, so now we want to find a path from 1 to n. And if you want to find a path which has all the vertices, what kind of path should it be? It's like this is kind of forced at this point. Like you don't even have to think of building a path.
It is like 1, 2, 3, 4 till n.
Biggest path.
Biggest path, exactly. Like you should just pick the largest path, right? Like not even just like a chain where you can keep building a path. It's like pick the largest possible path. And so again, so this is where I think the transition happens from thinking about it as chains versus immediately coming up with the maximum thing, is because sometimes the maximum thing is just forced on you. Like this is the best possible thing, and if this doesn't work, nothing else will work. But other times when it's not clear, then you have to build a chain, because that is how you figure out the insides of the problem. Like what is the structure, what's going on there. So maximal objects are some kind of end goal data structure in some ways. But in this case, the structure is obvious. Like this is what you have to do. So pick the longest path. U to V. Okay, now what? Now how do you go from here? You want this path to have all the vertices. Okay.
Suppose there is something outside of it.
Okay, pick a vertex W outside. Then what do we do? So if W is connected to two adjacent things, you would be done, right? Like it's connected to some vertex Ti and then to the next vertex Ti plus 1, then you can just squeeze W between both of them and increase the path length, right?
Yeah.
Yes.
Yes. So if you can find something like this, Ti plus 1, you can just push W inside and extend the path, but it's not very clear why such a thing should exist. So still a bit iffy right now. But okay, we should realize that we are removing n minus 2 edges out of n choose 2 edges. We are basically not touching the graph at all. We are like not even removing a full tree's worth of edges from the graph. So we are doing very minimal set of things on the graph. It should really be a full graph. There should be too many edges. So the main observation in this case is that degree of U plus degree of V itself is large enough. Is large. How large? Well, at least, so imagine you're connected to everything except the total number of missing edges. It's equal to n, right? So because you assume they're connected to n minus 1 things, n minus 1 things, and remove all the missing edges instead of just the common edges, just all the missing edges. So still at least n, like very big degree U plus degree V, which means that now, okay, I rushed a little bit onto this. Why should you even care about the degrees of U and V? The point is that there's an
Wait,
easier
how
way of
are
explaining.
you?
Yeah.
How are you getting that n?
Okay, I'll get to that a little bit later, but like let's just start with this. So Okay, inserting a W is hard, right? Finding two consecutive things and pushing a W is kind of hard. But there's a very obvious thing which is happening at the endpoints, which is that no neighbor of V can be added, and no neighbor of U can be added. So something is wrong with that, right? Like there's a problem when you do that, right? If no neighbor of V and no neighbor of U can be added, then all of them must already be there in the path in some order.
Yeah.
Yes,
So
there are at least like n in the path.
right.
So the path contains at least n steps.
Not so fast, because those two can have common neighbors as well, right? Like it's not like they're enemies or anything.
Okay.
So it's still a bit early to say that the path has length n. Like it's still a little bit early because they can have
Like
common
I'm
neighbors
saying
as
at
well.
least n.
Yeah, at least n. So now, yeah, right now they have at least n. Yeah. So this follows as follows. So imagine degree of U. It's connected to n-1 minus a few things, and degree of V n-1 minus a few things. So when you add the two degrees, you have 2 times n-1 minus a sum of a bunch of things, but none of them are the same things. None of them are the same edges, except possibly UV. So we'll talk about UV, I guess, a bit in a bit, but none of them are the same. So what happens is that you have 2 times n-1 minus a bunch of edges, which is a subset of the total number of edges you threw away, and you threw away n-2 edges. So whatever you're subtracting is smaller than n-2. So it's at least 2 times n-1 minus n-2, which is at least n. And the upshot of doing this is that if you look at neighbors of U like this, and you look at neighbors of V like this, then this bound itself, this n bound over here, tells you that there must be something like UI Vj somewhere, just by considering the length of the path. So the path has length at most n-1, we are assuming. So just by considering the length of the path, you can say that there are two consecutive things. Like there's something where U goes here, V goes here. In which case, or better yet, this is also true, but something else is true as well. Better yet, U goes here, and these are consecutive in the path. So you can start with UI, go to U, start with UI, go to U, go to VJ, go to V, and come back to UI. So the whole path is a cycle. It's just like a very twisted necklace kind of cycle, but it is a cycle. There's another case which we missed here was when UV itself was an edge. And that would also be a cycle. So either UV is an edge, in which case the bound is slightly weaker, but I think it still works because instead of n, you assume just n-2. And otherwise you have this, which also gives you a cycle. So the whole path is a cycle.
So cycle consists in exists in this graph.
Yeah. So there's a big cycle, not even a small cycle, like a very big cycle in this. And you have
Due
vertex
to
W.
our assumption of maximality.
Yes. And you have a W outside this cycle. So you just need some path from W to the cycle exists because the graph is connected, right? Like this condition is enough to make sure the graph is connected. Right? Because U and V will have a common neighbor always for any U and V. So if the graph is connected, you can find a path from W to somewhere inside the cycle, and then you can extend this cycle. So then you get a longer path. So all the vertices must be either in the cycle or it must be a path without the cycle element and just one edge. So that is your structure. In fact, that would also be the equality case as well. When you remove n-2 edges and leave just like one thing and leave the remaining clique of things, that is an equality case. So does everyone follow this?
Yeah.
Yeah. So the idea is that you look at this longest path, you can either force it to be a cycle or work around one edge. But in both cases, you'll get a cycle. And once you get a cycle, you pick a vertex outside, the graph is connected, you find a path towards the cycle, you get a longer path. So this is a very interesting way of creating a longer path. It's just like first making a cycle, then finding a path, creating something longer. Because if this was not a cycle, you can't extend it, right? Like if this was just a path and you only had W coming in at one place, you could not extend it both ways, right? But if this is a cycle, you can extend it and come back. So the reason you should expect to be able to do this in this problem is because there's way too many edges. You're only missing out n-2 edges. And if you look at the equality case and the case which the detector uses for the construction, that's why I think that case is interesting. It's kind of like this. It's kind of just like one edge removed. So the equality case is like an n-1 clique. And one vertex which just has one edge with the clique. That is the equality case. You're deleting n-2 edges from the exterior. And that equality case is very similar to what this argument leads to. It's like a very big cycle and then an even bigger path because you push this W towards the cycle. So many things, looking at the cycle, looking at the equality case, looking at the chain of paths, looking at the longest path because that's the only thing which can work. And then creating something out of that structure. So there's lots of ideas in this problem. I feel this is a bit too tricky. But yeah, I think there's other solutions as well, though. So this is not the only solution. There's a somewhat global solution by just counting things. There's a probabilistic method solution as well. There's a solution which starts with looking at the longest cycle. So there's many solutions. There's a solution with pure induction as well. So there's many solutions. This is just like one of the main solutions. Is everyone okay with this? Okay, so I'll stop now. Stop sharing. Any questions, feel free to ask.
Was that problem based on reality, like at least a
Yes.
bit?
What do you mean based on reality?
As in you saw that in some magic show or something?
Oh, no. I just always want to word a game problem as a magician versus a detective, and I like these guessing game kind of
okay,
questions.
Do you have some resource to suggest on making problems?
Making problems. I'm not terribly good at it. It's like just play with things you like, and if you like an idea, try to make it a problem, I guess.
Did you propose to this in Mo?
I can't say anything about that.
No, as in
He's asking about the
last year.
2022 one this year.
2022.
2022.
No, 2021. Okay,
2020.
yeah, it's 2022. Yeah, 2020.
2022. No, the 3-question one, right? No, not that one. So I
Yeah.
guess we can stop the recording and still chat a little bit. So we can close the recording now.
The recording ended.